Chapter 23, we are going to tie together three things. We're going to tie together stuff you learned in Chapter 18, sampling distribution models for means. We're going to tie together things about confidence intervals in Chapter 19 and Chapter 22. We do confidence intervals in both chapters. And then we're going to do confidence intervals today. So we're tying it all together, all these things that we've been doing. I told you it's going to start getting repetitive. And so if you know what was going on before, then you should know what's going on a little bit now. You should be able to help predict what's going to happen. All right? So back in Chapter 18, you had sampling distribution models. And it gave you a scenario, and you could use a normal model to find a probability at the end or whatever. After you checked a set of conditions, and you could draw the model, it would have a mean of whatever the mean was in the sample, because we assumed that the population and the sample had the same things going on. And then the standard deviation was sigma divided by the square root of n, right? Where sigma was the standard deviation of the population. Now, we had this discussion a few days ago when we were reviewing for your test. It's going to be really important to understand the difference between statistics and parameters today, because we have lots of stuff going on, lots of things to keep track of. So we talked about the other day that statistics in proportions, you had p hat as your statistic, and p as your population parameter. We're moving away from proportions for now, not forever, but just for now. And we're going to be talking about means. So remember that x bar or y bar or whatever variable with the bar over it is your mean from your sample. And mu, the Greek letter mu, is the mean from the population. Same thing, you have a standard deviation from your sample, which is s, and you have a standard deviation of what's happening in the population, which is lowercase sigma. You have to be able to know the difference. Now, I told you we're doing confidence intervals today. You know enough stuff about confidence intervals, you should be able to answer this question. When you're constructing a confidence interval, are you using sample data or population data? Sample data. It's based on a statistic. So, can I use this formula as it's written for a confidence interval? No, because I won't have what? I won't have sigma, right? If I'm basing an entire confidence interval on a sample, then there's no reason that I would have the population standard deviation. Like, why would I have that? Probably wouldn't. Okay? So, what do you think we're going to do instead? Find the standard error, which means we're going to do what? How's that formula going to change? Right. We're going to use S instead of sigma. We're going to estimate using the standard deviation of the sample instead of sigma, the standard deviation of the population. No big deal. We did that before. We estimated. We used p hat instead of p, right? Okay. Here's the problem. Normal models, if you remember, when we did this in sampling distribution stuff, we had a set of conditions, right? And the last condition was your sample size had to be large enough. And we'll talk more about that today, okay? But so generally, your sample sizes are going to affect that standard error because it's the square root of n in the bottom, right? And so if your sample size isn't large enough, then you can't use a normal model. And that becomes an issue. So I'm going to tell you a nice little story that's actually relevant to your life at the moment. Okay? There's this guy, William Gossett. This is a real dude. This is a real story. I'm not making this stuff up. Okay? It's in your book if you want to read about it. He was the quality control engineer at the Guinness Brewery like a century ago. All right? That's a pretty sweet job. So as quality control engineer, he's having to sample the batches to make sure they meet standards and specifications by the brewery before they send out those batches for consumption, right? So he's having to do samples. Obviously, if he's going to do that with any degree of care, he can't use large samples. Like, he can't sample 50 different, like, little glasses of Guinness. Like, that's going to get you nowhere, all right? You can't just keep drinking beer and do your job successfully. So he was using really small samples because he had to, right? So not a big deal. Well, so he was doing these small samples, and then he was saying, okay, this batch isn't up to up to standards, and then he would send it back, and then they would do more testing to make sure, and then most of the guys would be like, this is fine. So this is, like, you're making these mistakes. So pretty much he was doing a hypothesis test. He was rejecting the false null hypothesis, or say a true null hypothesis. So he was making all these type 1 errors, and he was making them a lot. All right, it was like 15% of the time. So that's costing the brewery money because you're sending it back, having them retest it, and then redo stuff, and then we're having to go through this whole process again. So he decides he's going to take some time off, and he's going to actually investigate this because he's actually interested in the statistics of what was happening because he's actually doing this like test. So he takes some time off and does some research, and he actually gets a degree in statistics in the meantime. So he's doing this research, he's figuring it all out. So what he realizes is, because he's using small samples, and he's using the standard error estimates and stuff, that he was having, and he's using the normal model like they thought they were supposed to, he realized that that is what was the problem. The small samples were not sufficient for using this model. So he realized that there was actually a whole set of models based on the sample size that he could use that were similar to a normal model, and that they were unimodal and they were symmetric and bell-shaped. They just weren't one model. It was completely based on what size sample you're using, what kind of shape it really had. So, figures this all out. So he's going to publish this because, duh, he made this awesome, figured this out. You're going to publish it and then be famous, right, for all time. So he goes and tells Guinness, I'm going to publish this stuff because I figured this out and I'm a genius. And Guinness really thought that he was going to like publish like trade secrets of Guinness Brewery. So they were like, no, you're not. You're not publishing this stuff. Sorry for you, man. So he had to publish it under a different name because they really thought that he was going to like give away how to make Guinness beer or something. I don't know. So even though William Gossett discovered this, and so it's his model, he named it the student T model because he was a student. That's the best he could come up with, not a creative guy. So you have students T model, which is a set of models. It's a family of models, all right? And they're all, again, symmetric and bell-shaped, unimodal. But then the smaller they get, the tails get more stretched out. So I've got a picture. It's not the best picture, but it's the best one I could find at the time. You have the Z distribution or the normal model in the middle in the blue. Okay? Unimodal and symmetric, no big deal. Then you have a T distribution, and here's two different ones. All right? So they're not the exact same, and there's actually one for each different sample size. So if you have a really small sample, it kind of makes this, I mean, it's still unimodal and symmetric and bell-shaped. It's just kind of really stretched out, right? This light lavender one. Then your sample size increases. It gets a little closer to the normal model, but it's still not. But again, unimodal, bell-shaped, symmetric, all right? So he's discovered that there are a set of models all dependent on the sample size. Now, every time we do anything now, we're talking about means, we're going to have to use the T distribution instead of the Z distribution. So we're tweaking some things we know. It's not a big deal. But because there is a different model for every single sample size, you have to indicate which model you're using every single time. So you indicate the model you're using by the degrees of freedom. And the degrees of freedom are just a fancy way of saying which model it is. All right? Different scenarios have different ways for you to calculate the degrees of freedom. Okay? We'll talk about that in a second when we get to what we're doing today. But you're going to be using T models for one sample, for two samples, for slope in chapter 27. You're going to be using T frequently. Okay? And in all of those, there's a different way to calculate what the degrees of freedom are. But again, the degrees of freedom is just a fancy name for which model you're having to use, because they all are a little bit different. Okay? Everyone with me so far? All right, so let's actually talk about confidence intervals. What do you know about confidence intervals now? Like, what are the 3 steps to a confidence interval? Conditions, mechanics, conclusion. same 3 steps apply here. I'm not ever changing those steps. Okay, so that's still the same. Now, we're going to tweak some of that, but same idea. What is that pattern we talked about from the formula sheet that a confidence interval should follow? What's that pattern from the formula sheet that it should follow, a confidence interval? Statistic, plus or minus, critical value, which before was z. It won't always be z, so we're going to call it the critical value. Multiply by the standard error, right, because we're making an estimate. So, in this case, it's going to follow the same pattern. But our statistic is no longer a proportion. Right? We're not dealing with percentages. We're dealing with means. So our statistic is going to be a mean. Our critical value, we just talked about this, is no longer going to be z because we're not dealing with a normal model anymore. We're dealing with a t distribution. So our critical value is going to be t star, not z star. All right? And then our standard error, we already have that formula. We know it was sigma over the square root of n. We've already said we're going to do the standard error. We're going to estimate with s over the square root of n. So you already have a basis and a background knowledge for what we're doing here. This is not brand new. That's why these chapters tend to go a little bit quicker, because you already should kind of know what you're going through. Shouldn't be this big change. So first step is conditions, right? There's only one condition that's different, but you already knew that from chapter 18. Okay, so we still have independence assumption. You're assuming that the people or the items or whatever you're talking about are independent of each other. You still have randomization. Is it randomly sampled? If not, is the group a good representation of the entire population? That still exists. The 10% condition still exists. Sometimes with means it doesn't make sense though, so sometimes we leave it out. It doesn't make sense in the context. 10% tends to be the less important one. Now, the last condition with proportions was success failure. How do you calculate success failure? What's greater than or equal to 10? Right, which is how they calculate it. N times P and N times Q, right? We don't have proportions, so we don't have P's and Q's anymore, so I can't do that. In chapter 18, we just kept saying, it's large enough, which is kind of, we were trying to like get through the chapter. We have a more specific condition here now. Okay, so for sample size, we have the nearly normal condition. We want our data to come from a distribution that's roughly unimodal and symmetric. Okay? Again, we know that our data in real life is not going to be exactly normal. It's not going to happen, but we want it to be unimodal and symmetric. So, here's what we're going to do. Your book's going to help you out. It's going to do one of 3 things. On the AP exam, it'll do the same thing. 1, they'll just tell you the data follows a normal distribution or follows a distribution that's unimodal and symmetric. So it tells you that. Then you know it's good. 2, they'll give you a graph. They'll give you a histogram or something that you can look at and say, well, my data comes from a nearly normal distribution. It's roughly symmetric unimodal. Or 3, they will give you the raw data in table form. If they give you the raw data in table form, which is generally what they do in the AP exam, I guess not generally, but they do that more often, how am I going to check to see if it's nearly normal? If they give you just data. I would use your calculator. So quick refresher, you have 2 options in your calculator. You would put your data into a list, so stat edit, there you go, put your stuff in a list. I've got some random numbers. I have no idea what they are anymore, but I have some random stuff, okay? But you'd have your data in a list. You would go and make a plot of the data. You have 2 options. 1, you make a histogram. You graph it. You always hit zoom 9. Again, I'm just saying this is random data. So this is obviously not nearly normal. It is skewed to one side, right? Skewed to the left. So in this case, my data would not be sufficient to use the methods we're talking about in this chapter. Okay, so that's one way. Second way, which I think is preferable because we have talked about histograms in the past. The zoom 9 feature on your calculator is making the bins all of equal width, and it's choosing that based on your range of your data. And we know as well, if we were just drawing a histogram, you can change the bin width to whatever you want it to be. And by changing the bar width, you can change what the histogram looks like, right? So histograms may or may not be the best way to look at things because they can be manipulated in that way. So your second option is to go to stat plot. We talked about this briefly. Underneath the histogram is the normal probability plot. A normal probability plot, if you have the data, should make a straight line. If your data makes a straight line, then you have data that's roughly unimodal and symmetric. So in this case, we already saw it was skewed to one side anyway. So you can see my data makes this really distinct curve here. That's not a straight line. Okay? So again, this data, which I don't remember what it is, just in my calculator, would not be sufficient for what we're doing here. Does that make sense? You want to check it. You just don't assume that everything's great and wonderful. You want to check it somehow. Maybe they give you the information, maybe they give you a graph, but you want to state somehow how you decided it was nearly normal. It is not just like, oh, for fun, I'm going to say this is it. We don't just assume that's happening. We actually look at it. Mm-hmm. You would say, looking at a normal probability plot of the data, or looking at a histogram of the data, I know that the data is roughly unimodal and symmetric, so the nearly normal condition is met. Okay? Questions about that? That's the only condition that's different. You have to work for that one a little bit, probably. Everyone go with the conditions. The next part is the mechanics. We already talked about this verbally, but here it is. We said it should be statistic plus or minus critical value times the standard error. So our statistic is a mean. Our standard error is S over the square root of n. Now, our critical value has n minus 1 degrees of freedom. So whatever your sample size is, minus 1 is the degrees of freedom. Again, the degrees of freedom is the fancy way of saying which model in the T family you're using, because there is a different one for every single sample size. We can talk about how to find all those things in a second. But any questions about the actual formula? It's really similar to what we've done before. Notice the name is a one sample T interval. We're doing the interval based on one sample. It would be weird to say one mean. That's weird. Like we do one proportion, but this is like one mean. We're basing it on one sample. So one sample, and I say T interval because we're using a T critical value. As a side note, we can get into this later. Sometimes they try to trick you on the AP exam / in your textbook. If for some reason they decide to grace you with the standard deviation of the population because they're being nice, then there's no need to estimate the standard error because you can find the standard deviation. And so then you would use Z instead of T. You would use a Z critical value, right? Because that would follow a normal model, not a T model from chapter 18. If you're going to estimate, like we're going to have to do most of the time, you use S and T. Okay? So this is rare. That's a side note, but it can come up. This is where it comes up the most. In the multiple choice on the AP exam, they'll say, in which of the following situations is it appropriate to use a Z critical value or a normal model? They'll give you a bunch of scenarios, and one of them is you know the standard deviation of the population. Okay, so it's just a matter of knowing that. So I want to make sure I mention it, but it doesn't come up very often. Any questions about what the interval is supposed to look like? So we talked about the conditions, looked at the mechanics. The last part then is the conclusion. And the conclusion follows generally the same pattern we've been talking about. I'm going to do this part first, and then we'll go back. All right, so let's talk about the conclusion, because this is where we're going to talk about conclusion. It says the medical researcher measured the pulse rates and beats per minute of a sample of randomly selected adults and found the following students' T-based confidence interval. So a 95% confidence interval, and it gives me the interval. Again, the whole entire purpose of a confidence interval is to trap the true parameter. So in this case, I'm trying to trap the true mean pulse. Okay? It's got to be somewhere in here. We don't have percentages anymore, so don't try to make this 70.9%. It's not what it is. That's 70.9 beats per minute. Right? It actually has units. So get out of the mindset of percentages. So A says explain carefully what the software output means. That just means let's go through and say what the interval means. So give the conclusion. So how do our conclusions for intervals always start? Yep. So same thing. I am 95% confident. Almost. The true average pulse. So in this case, we're not talking about proportions. So you're talking about the true average, whatever we're looking for. We're trying to find the true population mean. Average pulse is between 70.9 and 74.5 beats per minute. You want to make sure you include units because we're not talking about percentages anymore. So it's got to be between something and something what? Okay? You can't just say it was between 70.9 and 74.5. It's got to have something. So that's not a big deal, right? Conclusion really hasn't changed. We're good with that. Okay, part B says, what's the margin of error for this interval? So we've got some vocabulary here. It came up on your test as well. You have the margin of error, and you have the standard error. What does the margin of error mean versus the standard error? Okay, margin of error is everything after the plus minus. So it's what you added and subtracted to that mean value that was given in the sample. What's the standard error? In this case, S over the square root of n, right? So be careful that you know that. Some of you guys missed a multiple choice question on the last test because you just didn't know what standard error meant. You did the margin of error instead. And that was one of the choices. Tricky, tricky. Yeah, so standard error would be just this part, and then margin of error would be all of this together. Just throwing it out there to the universe. That would be the margin of error, yep. Did you fix it? All right, so in part B says, what's the margin of error for this interval? I need to know what I added and subtracted to the sample mean, right? There's a few ways to approach this. Someone give me some way we try to find the margin of error here. We have the two endpoints of the interval. So one way to approach it is we find the average of the interval because that's the mean from the sample, right? That's the middle that we would have had to plus minus something to. So we can do it that way. So if we're doing that, we have y bar, whatever that value was, is the endpoints averaged together. Does that make sense to everybody? That would give me the exact middle of the interval. Yes? And I'm just going to write it down because typing things in my calculator takes too long. Because that's the exact middle. That's not what the question asked. We had to do that first. The question asks for the margin of error. So if I was doing the confidence interval, I would take 72.692 plus or minus some number to get these two endpoints. So how can I find that number? It's not a trick question. Yeah. Subtract this mean from the upper endpoint, or subtract the lower endpoint from the mean, right? Either or, you're going to get the same value. So 74.497 blah, 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 minus 72.692 ends up being 1.81. If you add and subtract 1.81-ish, I rounded, obviously, then we can get the two endpoints, right? That's the margin of error. That shouldn't be a super hard question to answer as long as you know what that means. What's the margin of error? Questions about that? Then the last one's just a thinking question. We have a 95% confidence interval. If we wanted a 99% confidence interval, would the margin of error be larger or smaller? We're going from 95 to 99. 95, 99. So the interval will be wider, so the margin of error will be larger. All right, so think about that middle percentage. Okay? Questions on A, B, or C? All right, let's go back and talk about this whole T part. The next question we're going to do an entire confidence interval. We haven't talked about how to get this T critical value situation going yet. So, using T tables, there's tables that exist for everything we've done in here, normal models, T distributions. I don't use them because you have your calculator. Software or a calculator, so we're going to use a calculator, obviously. The critical value of T for a 90% confidence interval with degrees of freedom equals 17. Now, before we do this, what was a 90% confidence interval for Z? Right, 90. So 0.5. So you did inverse norm of 0.05, and you got 1.645, right? Everyone remembers how we did that? Right. We do the same thing for T. It's just not inverse norm. So 90% confidence means there's 10% left over. There's 5% on each side, right? So we have inverse T, that exists. And we put in our area still, so 0.05. But we also have to identify the degrees of freedom. That just tells you what sample size we had and how we're going to get it. So remember, degrees of freedom was n minus 1. So what was the sample size originally on A? Degrees of freedom is n minus 1. So 18. 18. All right, so our sample size is 18, so our degrees of freedom is 17. So you go to your calculator. Anyone have an 83 in here? No. I'll have to program yours. You don't have an inverse T, so I'm going to actually write a program in your calculator. Okay, so if you go to your distribution menu, underneath the 3 normal distributions, there's 3 T distribution question stuff. There's inverse T, T-PDF, and T-CDF. Correct me if I'm wrong, if you have the 83, you have the T-CDF part, you just don't have the inverse T part, I think. All right, so go to inverse T. Mine keeps going back and forth between being updated and not today, for whatever reason. Yeah. So we're putting in the area, so it's 0.05. Everyone know where the 0.05 came from? And our degrees of freedom is 17. And it'll take it a while to think. And we get 1.74. please note that's not the same as Z. It shouldn't be. So don't try to use the Z critical values memorized because they won't be right. All right. Questions about that? We're going to come back to do that again in a second. I'm assuming you could do B then. You could go through and figure the next one out. What would the area be? Like what would be you type in the calculator? What would the area, like that number be? 0.01, right? And then we have degrees of freedom 88. They gave it to us. All right. So we know how to calculate the T critical value now. That's good. On number 3, describe how the shape, center, and spread of T models changes as the number of degrees of freedom increases. I'm going to reference this picture again. If your degrees of freedom are increasing, what's happening to your sample size? What's happening to sample size? It's getting bigger, right? Degrees of freedom is just n minus 1. So if your degrees of freedom are increasing, that means your sample size is increasing. Okay? So if we look at this, if we have an n smaller than 30, we have this distribution right here. And if we get close to 30, we get this distribution right here. So what's happening the larger your sample size gets? Right, it's getting closer to the normal model. So your center is staying the exact same, right? The shape, it's getting more closely related to the normal model. And the spread, you guys could have told me this before because we talked about it a million times. If you increase sample size, what happens to the variability? It decreases, which means the spread decreases, which is why it's getting more narrow. Right? So shape gets a little more unimodal and symmetric, closer to a normal model. The center stays the same, and the spread decreases. Because we're increasing sample size, we decrease variability. Questions about that? Describe how the critical value of T for a 95% confidence interval changes as the number of degrees of freedom increases. Again, degrees of freedom increasing means sample size is increasing. I want to make a note. What is the Z critical value for 95%? 1.96. We just talked about number 3, that as your sample size increases, that you get closer to the normal model, right? So what do you think is going to happen to T as the sample size increases? If we're increasing the sample size and our model is approaching a normal model, then what do you think is going to happen to our T critical value, the larger the sample size gets? It'll get closer to 1.96. It should, right? If it's getting closer to a normal model, then the larger the sample size is, the closer it gets to 1.96. Now you could try that out in your calculator. Inverse T 0.025. Let's start with a sample size that's small. So let's start with a sample size of 6. So degrees of freedom is 5. It takes it for everything. 2.57. And then if we increase the sample size, so let's do 60. 2. Getting closer. So I said 100 earlier, so let's say 101 so I can actually type in 100 degrees of freedom. .98, we're getting closer, right? So the larger our sample size gets, the closer that model is getting to a normal model anyway, and so the closer our T critical value is to getting to Z. Question. All right, everyone knows, though, how to find the T critical value now, though. Okay. So then let's do an example. We'll do it quick. Researcher described in exercise 9 also measured the body temperatures of that randomly selected group of adults. Here are the summaries of the data he collected. We wish to estimate the average temperature among the adult population. Now, A, B, and C are all the stuff we would normally do for our confidence interval. Okay? I just split it up for it. So check the conditions. Is each adult independent of the other? There's no reason to assume that they aren't, right? Okay, is it a randomly selected group of adults? Yes. Is 52 is our sample size? Is 52 less than 10% of all adults? Well, let's hope so. Oh my gosh. All right, then the last one is nearly normal. So you've got some things to look at. If we look at the histogram, is this roughly unimodal and symmetric? Rough. So we could also look, though, at the mean and the median. Way back, I mean like way back, in chapter 4, chapter 5, we talked about the mean and the median. If the mean and the median were close together, what did that mean? We said that we would say it's roughly symmetric if they were close together. Well, so they look really close together, so roughly symmetric, right? If one was far away from the other, we would say it's really skewed. But so in this case, the sample size is 52, so that's kind of large. Plus the mean and the median are close together, so I would say that the nearly normal condition is met because of those reasons. Is that okay? Because the sample size is 50, and because the mean and the median are close together, we would assume it's symmetric. Like if you had 98.2 and 96.4. Right. Now, after you check the conditions, you write me a sentence, right? So because the conditions are met, we can construct a one sample t interval. This is why I tell you to keep track of all these things. One sample t interval. All right. For then the 98% confidence interval, we have y bar plus or minus t critical value n minus 1 times the standard error. What's the mean, and how did I figure that out? It's right there. 98.285. Plus or minus, we'll do t in a second. Standard error is s over the square root of n. So what is s? Oh, look right there. And what's n? 52, because it's right there. Now, we're doing a 98% confidence interval. Again, there is no memorizing. We just did 98% confidence interval before, but it changes for every single sample size. So you always have to calculate it every time. So 0.01 degrees of freedom is how many? 51. N minus 1. So we get 2.4. All right. Questions about that? To save time, since we're running out of time, can I just tell you what the interval is? Because you can do the math, right? We have 98.058 to 98.512. Degrees. Okay. C says explain the meaning of that interval. I am 98% confident that the true average body temperature, not the true body temperature, the true average, talk about means. It's always an average. The true average body temperature is between 98.06 degrees and 98.51 degrees Fahrenheit. Questions about the conclusion? D says explain what 98% confidence means in this context. So going back, this is not the conclusion. What does 98% confidence mean in general?
98% confidence. Probably should use the
No. 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 No.
And how confident you are that the reality matches is within the
Sort of.
sample of according to the rotten day.
How about this? If you sampled over and over again, then 98% of the samples would end up with intervals that contained the average body temperature. So in repeated sampling, 98% of your samples would lead to intervals that contained the true average body temperature. Okay. E, 98.6 is commonly assumed to be normal. Do these data suggest otherwise? And explain.
Yes, because it is outside the interval.
Way to go, man. Yes, 98.6 is outside of our interval, so our data suggests that the average body temperature is actually less than 98.6.
Yeah, is it?
Ask Mr. Chipman. He teaches biology. It's always based on some real study, but it's based on one sample of 52 people as well.
Well, yeah, but
It doesn't say. Couldn't tell you. You never know. All right, questions about that? I've got one more thing to talk about really fast. Any questions about this one? I know. Okay, this really quick. This is not computing things so much. I'm just going to make a point.
okay, no.
Would a 90% confidence interval be wider or narrower than 98%?
One of them.
Narrower. If you have a 98% confidence interval and you narrow it to 90, get a narrower interval. What is one advantage to a 98% confidence interval? More confident. What is a disadvantage?
You're like super broad.
Your interval.
I'm 100% confident that it exists.
Right, your interval is wider, and so it's not as helpful. Okay? I'm almost done, I promise. If we conduct further research, this time using a sample of 500 adults, how would you expect the 98% confidence interval to change? What happens when you increase sample size? Decrease variability. So what happens to the margin of error?
It goes down.
It goes down. So what happens to your interval?
It goes down.
It goes narrower. Right, the error is smaller, so you're adding and subtracting less. All right, this is the point I really need to make, though, right here. How large a sample might allow you to estimate the mean body temperature to within 0.1 degrees with 98% confidence? We did this in Chapter 19. We found sample size. So we said, okay, the margin of error is equal to what's after the plus minus sign. And so we could fill this in. They want within 0.1 degrees. We actually have an S from the last question. These are both related, so 0.6824. How am I going to find T? What's the problem? What's the problem? I need to know N to do N minus 1 to figure out the degrees of freedom to figure out what T is. So, because of that, you're always making an estimate anyway, right? So because of that, in this scenario only, if you're trying to find a sample size, you can't use T because there's no way to figure out the degrees of freedom. That's a problem. So you're going to estimate using Z. Great. All right, does that make sense to everyone? Right, that's an issue that we have to overcome, so we have to use Z. All right, here is your assignment.